This is a short 5-minute summary video detailing the findings in a paper that I published in collaboration with Dr. Sean Walton of Swansea University's College of Science back in 2017. The title of the paper is Aerodynamic Optimization of a Hypersonic Reentry Vehicle based on solution of the Boltzmann-BGK equation and evolutionary optimization. And essentially what we did, or the work behind this paper, was the application of a molecular gas dynamics solver for solving rarefied gas flow problems applied to a hypersonic reentry vehicle, and then that CFD solver was coupled to an evolutionary optimization algorithm based on modified cuckoo search to find the optimum configuration for the reentry of this hypothetical vehicle for different optimization objective functions. And this work was published in Applied Mathematical Modeling, the journal Applied Mathematical Modeling. So because the application that we're interested in is an upper atmosphere case, we're looking at re-entry of a space vehicle akin to a space shuttle. The underlying governing equation of relevance is the Boltzmann equation. We need a molecular description of the fluid dynamics because the Knudsen number of this problem is larger than the continuum hypothesis, or larger than that is allowed to apply the continuum hypothesis upon which the Euler and Navier-Stokes equations are based upon. So we've used the BGK form of the Boltzmann equation. So the BGK form approximates the right-hand side collision term of the full Boltzmann equation by assuming that departures from thermodynamic equilibrium are small enough that we can say that the effect of molecular collisions is simply to push the molecular distribution function of the molecules back towards the Maxwellian form. So that's the F0 on the right-hand side of this equation at a rate proportional to the molecular collision frequency at that point in space, which is the nu on the right-hand side of that equation. The paper explains fully the discretization approach and the CFD method behind this, and refers back to some papers that are solely focused on the CFD solution approach. But in essence, the physical space of the problem is discretized using an assembly of discontinuous triangular cells. The velocity space element of the spatial discretization is done using a single high-order element. And then a two-step Taylor-Galerkin approach is used to discretize the governing equation, the Boltzmann-BGK equation itself. Before moving on to the main focus of the paper, which of course is the hypersonic optimization problem, the solver is tested against some known benchmark solutions. The first case that is considered is a Riemann type problem where we have an interface, a gas on one side, a vacuum on the other, and the gas is allowed to expand into the vacuum, and we use the solver to track that interface and look at the solution. There's an analytical solution to this problem which the computational results compare well against. And then the solver was run and compared to a continuum problem and continuum Navier-Stokes based CFD solutions of low supersonic flow, so Mach 1.5 flow over NACA 0012 aerofoil, and shock position and jumps in properties across the shock and so on are compared with continuum solver solutions. But the main bulk of the paper then explores the response of the optimizer to which the CFD solver is coupled by changing the optimization objective function. So the parameters in the optimization, the kind of design parameters, are 5 values, the major and minor axes of the two ellipses that define the geometry and the angle of attack of the geometry on re-entry. And we use the optimizer to search the optimum combination of those design parameters for different objectives. So we vary and look at things like how do you maximize the drag, how do you minimize the drag, and I guess the one that's of most interest is how do you maximize the drag, i.e. provide the maximum amount of deceleration for minimum temperature increase at the surface of the body. And the details of the findings we get from that, of course, are in the paper. So if you want to find out more about this work was published in the Journal of Applied Mathematical Modelling back in 2017, and the details are here on this slide.